All right, folks, let's get started. So today's topic is basically all the stuff we need to know to be able to do the homework that's due in a couple of weeks. And as it happens, in 385, they're doing almost the same homework.
In C++.
In C++, okay, whatever. What's that?
Don't they have more commands and do it like 2 p.m. today?
Oh, it's due today. Oh, that's a little, okay. They won't have much help of from what we're doing then. I was thinking, welcome all the 385 people on the video here so they can, learn a little bit about the various functions. But
They're probably working on it right now.
yeah, it's too late. Okay, never mind. Yeah, so the reason that it's like that is that this is the first time 361 is offered. This is also the last time 385 is offered in the shape that it is now. So when you take 385, you're not going to be doing the shell again. Fingers crossed.
What we're going to be doing?
The idea is that it's going to be mostly operating systems things, so that's in the kernel rather than in user space where we're now. So, but this is not nailed down yet, so we'll see. Okay, so we have quite a bit of ground to cover today, but the stuff is not all that. Most of it is not all that complicated. Still, I thought we'll sort of try going through the various motions that we need for the homework, but it's not going to be all put together, and then we can try to understand what's going on along the way. So, things we will be covering. Of course, we've done fork already. Or we'll maybe discuss what that's all about. Okay, maybe we'll call this important function calls. So fork, we'll be dealing with pipe, which is a very important one. We'll worry about dup2. And then maybe, of course, we'll do a little bit of wait to try to understand that, and I don't think there's that much more. Maybe some string stuff, but we might skip that. Okay, so fork, of course, is for I miss one very important one. Exec, and maybe get end might be important too. All right, so I don't know if we'll go through all of these, but you'll certainly be using all those in the homework. So fork, of course, is to make a copy of yourself. But that's not very handy. Right? If you want to run some other program, that's not yourself. So clearly, we're going to need to do something about that. That's execve, is to kill yourself and dedicate all your resources to this other binary. So now that binary gets your process ID, and your address space, all that is wiped away. Your stack is gone. Everything about you is gone except your file descriptors. And your process ID, and you're now replaced by whatever program you call there. Okay, so that seems a little drastic, but that's just the way things work. So you first duplicate yourself to create a new process, and then you manipulate the file descriptors a little bit. That could be handy to say, this process that I'm about to become, it should. All its output should go here or there, right? Okay, so that's execve, and then get end. That's to read these environment variables. So on the shell, you might say, on the command line, you might say set. For example, you see all these variables. Get end lets you access those variables. The only one we really care about right now is this one, of course, path. So we'll see what that's for as well. And then pipe, that creates new file descriptors. So you have we usually have the standard in, standard out, standard error. You can make a new one by using open, right, to open a file. Actually, I'll just put that one in here too. Open connects a file descriptor to an actual file, right? So you create a new file, and then you have a number that refers to something that then refers to that file, right? But if you don't want a file in the back, you want to talk to another process, then what you do is you create a pipe. The pipe has an input and an output, and then if you write to the input, it comes out. Someone can read from the output. So you hand one of these, one of the ends of the pipe, you hand that off to some other process, and you start writing on your on the input end of the pipe, and then the other process can read from the output end of it. So there isn't really a good way using pipes to say attach to an existing process. What you do is with pipes, it's always about creating a new process that is on creation attached to your process through this pipe. If you want to talk to an existing process, then we use sockets, and we'll deal with that a little bit later. And you'll deal with that a lot in 450 for sure. Networking, yeah. But sockets don't have to be for networking, and there's not that much networking about sockets. It's just that you use them a lot in the network course. Just talking to programs on the same computer.
Oh, sure.
So programs on the computer, they like to talk to each other, and they do it via sockets, oftentimes. Okay, and then this is a hairy one. So in order to understand DUP2, we really need to understand how file descriptors work. So let's, I think we'll have to draw something. That's not it. That's my garden. So we'll close that. Okay, so yeah, it looks suspiciously like that, but let's draw a new one anyway. So in every process, so let's say we have a couple of processes here. Process 1, process 2. For every process, there is an array sitting somewhere in kernel space. So this is, actually, maybe we draw a dividing line here. Here's user space. Here's kernel. Every one of them has a table like this. Maybe make it a little bit larger, like that, with a bunch of structs in them. So there's one. Here's my standard in, standard out, standard error. And these are actually standard error. And these are structs with a bunch of information in them. Right, saying what does this, okay, maybe I should write here file descriptor table. So there's a bunch of information about what's going on with standard in at the moment. If I open a new file, call it F shows up over here, and in particularly for an open file, it'll be which file, how far into it. Right, that's typically what a file descriptor says. Which file are we reading and how far have we read so far? Sort of the offset into the file. Yeah.
We also have read-write permissions.
Yes, so there will be flags about if we're allowed to write to it. That's a good point. So I'll just say flags. Okay. For standard in, it doesn't work quite the same because there isn't an offset quite, but on the other hand, there might be probably something saying, which pipe? So there's some pointer to a pipe, and then maybe is there something to read? Perhaps. So I'm not 100% about that, but I think there might be state like that in there. Okay, so this is just an array. So in the user space side, we just refer to these by numbers, right? How far down. So standard in is 0 because it's the first entry into that array. All right, so now there's a couple more things here in the textbook, and I thought it was kind of elegant, so we'll just describe that as well. There's another data structure back here, which perhaps how do we go? So I think it's called a V table, but we can ignore that. So this is actually a file table. So I think it's called a V table, but I'm not sure. At least in the textbook, it may have been called a V table. It's not called that in the Linux kernel, I believe. So now there's this which file part. It says, okay, I'm talking to this file, and here's some info about a file. Right? So where is it on the disk? Do I have any pieces of it cached in memory? Things like that. So now I might have two file descriptors. Another, so we call it FD1 and FD2 instead. They might refer to the same, and now I have to change my strange lines here. I don't know what's going on with them. Let's see. Not exactly what I meant to make, so we'll go straight, maybe with a arrow. Okay. So now both of these point to the same. How do we do it? Oh, I think we can go like that. Let's see. Whoa, that is cool, huh? Okay. So now both of these file descriptors, they both point to the same table that has information about the file. So if we read the file a little bit, now some of that is cached. If another file descriptor comes in and wants to read from the same file, of course it'll read from the same cache. Right? So there isn't any duplication about the files, but there will be some other state for the second file descriptor that might be different. So we can have two file descriptors for the same file. We'll start reading for a while, and then we can start reading from the beginning again on the second file descriptor. So don't confuse file descriptors with actual files. That's all. And this actually goes a little further, because now for every process we have one of these tables. Right? So there's nothing really in common between the standard in here and the standard in there, except that they happen to be the first entry in the table. Of course, we can actually change this around if we want. So the standard in here doesn't have to be a pipe. Right now it says like a pipe probably to the output on the command line, right? Or of the input from the command line. But if we want, we can stick something else in there. So we can stick a file descriptor. So like temp out. Oh, not out. In maybe. Better. Because that was standard in. Right? So if I overwrite the entry over here to refer to something else, some file, then the program is still going to talk to 0. Right? Whenever the program runs, say, get s to get the next line, it's just going to look at the 0th entry in here and get the next line from that entry. Okay, so that's file redirection, or input-output redirection in general. We're just playing with the contents of these entries. Okay, so that brings us back to dup2 then. If we want to change something around, say we want to now, we want to do this redirection. Actually, this is a little less common, so let's do the other one. Say I want to run a program, but all of its output should go into a file. Right? Then I first open the file, so I get a file descriptor for some new file. Oh, I clear this out, I call it FD1. So now I'll open the file, and this refers to the file. That's not good enough. So now I fork, right, and I open the file, and then I want to exec, to run ls, let's say. Nothing's going to happen. ls is still going to have this file descriptor in there. But ls doesn't know about that file descriptor. It doesn't care. ls just tries to write to standard out. Right? So if we want ls to be writing its output to FP1, what do we need to do? Well, we need to copy the contents of this to this location in the table, right, in the array. And that's what dup2 is for. So if I run dup2, and I say which, let's say, from FD, from index to index. So now if I say dup2, what is that, 3 to 1, right, they start at 0. oh sorry, that's dup2. I run dup2 like this, then I will end up with a copy of FD1 over here. Oh. Right, so whatever FD1 was pointing at, standard out is also now referring to the same place. Yeah.
Is dup2 temporary so that if you stop using the app, it returns standard out, or is it always going to be FD1?
You're stuck with it. But that's for the process that we're currently running. So if we're forking, right, now you have copies of these tables. So I started out maybe with this one, and then I fork, I have another one that looks exactly the same down here. And then I overwrite FD1 up to standard out. That doesn't affect the original process. So then at some point, I'm done with ls. ls kills itself, right? No process can just, they can't just return, they actually have to ask the OS to kill them with this exit. So eventually it kills itself, and then we forget about all of this, right? So we're just back to the original. Okay.
Say you wanted to put standard out back in that slot.
Hmm.
Seeing as you no longer have standard out, how would you do that?
Yeah, then it's gone. You can't do it. But you could save it ahead of time, right? So you could call dup2 before you do this thing. You could call dup2 over here, let's say. There's actually another one called dup for that. So dup2 takes a destination. Just dup for duplicate. Let's say from index. Actually returns a to index. Right. So now you have a. If you call dup2 and you only have these three, then it ends up over here. So. Okay, so that's unusual. Usually you don't want to do that, but it does happen. Okay, so let's just think about what happens when you call pipe instead. So let's return this to the original here. So now I run pipe, and let's take a look at the. That's not the right one. This is some email delivery thing. Okay, so we want to watch out for this sort of stuff. If you don't get something that seems reasonable, just add the chapter number there. Okay, so here we are. Pipe takes. What is this? Yeah, except it's ints. And that's all file descriptors from user space that look like ints, but they're not actually file descriptors, right? They are indices into this file descriptor table that we never actually get to see the actual file descriptor. But there's something curious about this, because look, it looks like it takes an array.
Is it maybe to and from as an array instead of just taking two arguments?
This is correct. What I'm curious about here is that C does not support passing arrays around. There isn't such a thing as a function that takes an array as an argument. You can only take a pointer as an argument. So they're being helpful here. Right? They're saying, oh, you are supposed to send in a pointer to an array of length 2. Right? But it's not actually going to check that it is an array of length 2, because it can't. Okay, so you pass in a pointer to an array with 2 ints in it, and pipe is going to fill in those 2 ints. What are the ints? Well, obviously 2 indices into this array. The first one is the read end, right? The read end of the pipe. So call it pipe 0, and the second one is pipe 1. So that's the second one, then is the right end of it. Okay, so when I call pipe from any process, this is what ends up in my file descriptor table. So now I have these two. They're like any other file descriptor, so I can say read from it, I can write from it, I can close it, I can't really open them, but I can printf to it, things like this. So, actually, can I printf to it? No, I can't. So anyway, it doesn't really do much yet, because we don't have any communication set up with another process. So what I could do, if I want, is I can write to pipe 1, and then later on I can go and read from pipe 0. Right? And then I'll get whatever I wrote. It doesn't seem very convenient. Right? Actually, how does that even work? So where is that all stored then? I write something to the pipe, but it's supposed to come out here. I'm not even sure you can do it. It could very well be, depending on how much you write, it could very well be that it'll block. Your write call will block. Nothing's going to happen until someone starts reading from pipe 0. If you write a little bit, that's not true. There's a buffer in the OS, so it'll actually keep that for you. But if you write a lot, it's just going to stop. Okay, so if we now want to talk to some other process through this, all we can do is fork ourselves after we've created the pipe. So now we get a copy of this, right, in a new process. Okay, kill these off. Now we have a new process with another set of this, and we're wanting the one process to write to it and another process to read from it. Let's say we want to see the output from our child here. So we started a child, this is the child. Right. So what do? Well, in the child, before we exec v, before we start a new binary, we have the child reconfigure itself. So the right end, that was this pipe 1, goes into standard out. Actually, it can stay over there too. Okay, and then on the read end, well, we have two choices. Right? If we just want to play with it ourselves, right? We're not starting another program here. We just want to see whatever the process says. Well, then we read from pipe 0 and we're good. But if we want to start yet another process, now we might redirect now. So we say, oh, this other process, say it's grep or something that filters input. You want to take pipe 0, put that over there, and then we exec v. Now we run our grep on there. So if I was doing, for example, ls grep awk, right, like that. Now I would have to redirect first the ls, that's the second, that's the child. Right? So it writes to the pipe. There's the pipe. And then I redirect. For my other fork, I redirect the input from the pipe into standard in and run grep. Okay, so that's what I wanted to try now. But first, questions on this? There's a lot of stuff going on here, and there's more to it, as you'll find out. Sometimes a program is not going to quit until its input is gone. Let's see an example of this. So this is, we probably won't get through all of that today. In fact, there's no way we can cover all the little special cases that you'll run into in the homework. But say I run cat here. So how does cat work? If I say hello, cat says hello, right? So now, see, it's not quitting. This program just keeps running. When will it quit? Well, it quit when I stop giving it input. So in this shell, I can hit Control D to say, oh, there's no more input coming. And that finishes cat as well. So now if you have a program like grep here, grep does the same thing. Let's try this. If I say hello, it prints it out. If I say hi, it doesn't print anything. Right? Same thing. It's reading from standard in, and then it's filtering it based on the command line arguments. So now, what if I'm running now, what our example here, we were saying ls grep awk. That's what we were doing over here. So now, there's actually two handles, or three handles on this end, and three handles here on this end on the pipe. So we know our grep, this piece, isn't going to finish before the input is done. What does it mean for the input to be done? It's someone has closed the other end of the pipe. So the input is pipe 0. We're reading from pipe 0. Pipe 1 then has to be closed. Okay, so ls, if we're running ls here, ls automatically, when it shuts down, it closes its pipes, closes all file descriptors, everything's done. But there's a remaining problem here. Can anyone see it? No? The pipe isn't quite closed yet. Because there's another handle here. Right? That's the right end of the pipe. So now, after ls quits, it's done writing to the pipe, but there's someone else holding on to the right end of the pipe too. That's grep. Grep is really supposed to be concerned with the read end of the pipe, but we forgot. We made the pipe and we forked, and now there's a stray file handle over here. So now grep is going to wait for itself to finish. How long is that going to take? That'll take forever. Yes. So the only way to solve this is to proactively close this pipe one. So before we start up our grep, we have to make sure we close this file descriptor, because otherwise we'll always be waiting for the pipe to disappear. Okay, let's take that for a spin then. There's a lot of little pieces to making a shell, but those are pretty much it. Yeah, there's maybe one or two other weird things. Okay, let's see. So I'll just do it on... my VM died for some reason. My virtual machine on the computer died, so I'll just do it on the Mac. But it works exactly the same. This is all POSIX, standard Unix stuff. No, let's call it pipe. Okay, so we're going to need a few includes. I have a few includes prepared. Alright, standard I/O, everyone knows that. This one has the dupe2 and the pipe and the dupe. And then we'll need wait eventually as well. Okay, so same old. So my idea here was that we're going to make a program that is actually a composite of two programs. So we're not making a shell here, but I'm making a program that what does it do? It is ls, but there's a grep after. Okay, so it takes all the command line parameters, passes them to ls, but then it greps and only shows anything that matches .c. Okay. So first of all, then we want to probably make a. Let's start by making a child. So we want to run both ls and grep. And actually, our program isn't going to be, doesn't need to be active anymore, right? We just want to run ls and grep, and we don't need to do much. So we can just kill ourselves proactively here. We'll replace ourselves with ls. So here we go. The first child then is, well, a child is created. If we got PID, then that means we're the parent. So if we got a value back, we got the child's process ID. That means we are the first one. Right? We're making this pipe, ls, and then a grep. So let's see. What do we do? Here, if we got something, then we are ls. Right. Otherwise, become grep. Okay. Okay, and so let's looks like VE. Here's a tricky one. It's not enough to just run ls because that doesn't mean anything. You have to specify a full path. So to get the full path, we either figure it out ourselves, which is what we're doing here. So I say which ls, and it's in bin ls. Okay, so that's fair enough when you're hard coding something like we're doing now. In other cases, you're gonna want to use getEnv and then loop through the whole environment variable, that getEnv path really, and then loop through all of those potential paths and find the first ls in any one of those paths.
Could you technically route the output of which to your program save the output.
Let me see if which is which. Ah, yes. Technically, I suppose you could. I wouldn't recommend it. Right. Okay. So we want to run a program. So execve takes a couple other parameters. Right. It takes the path, and then, surprise, surprise, our argv. Okay. So those are the command line parameters. We have command line parameters already. They're passed in here. Except I didn't declare them.
Even if you don't declare it, pretend as if you did it.
No.
No?
Because I actually want to use them. It doesn't pretend like you declared them, it just ignores it, because in C, these things actually don't show up in the binary anyway. And since I didn't use them, it's no problem. But here, I actually want to refer to them. I have to give them a name. So here I'm saying argv, and then I'm not going to pass it any environment variables. So I just give it a 0 there. Okay, so this actually creates now our process, and I think we should be good to get started at least. I call it pipe.c. Look at that. Okay, so what happened? We forked for some reason. It hasn't done anything good yet. And then we ran ls. But let's try a couple of things here. And then all right, any thoughts? Let me go to another. Okay, so I made a little directory so it doesn't get too confusing. What are we going to get? What kind of output are we going to get here? So at some point we're going to get the output from ls, of course. We're going to get this printf and so on. But which one comes first?
I assume we get hello before ls, hello after ls, and then the x and the output.
Let's see. Okay, so the first guess here is we get hello before ls, and then the output of this, or no, and then we get this, and then we get the output of that. Okay, and what about this one?
First, afterwards.
Okay, first, afterwards. Actually, it's undefined.
Yeah.
Okay, so it can go either way, because here we're splitting, and now we have two programs running, and it depends on the OS if it decides to run one process or the other one first, or something like that. Fortunately, with printf, they're not going to come at the same time. They're not going to mix into the same line. Printf is nice enough to split it into lines and have them well separated. Okay, but there's one more confusion. Actually, okay, so this one comes before or after, we don't know. Or it could come in between. All right? But what about this here? Harry had one suggestion. I would like to have more suggestions here. So clearly, hello before is going to come first. And that seems pretty obvious. But then what? Then we get the output of ls. But that one, actually, we'd never get.
Yeah.
Because we just killed ourselves. Right? We just replaced ourselves with ls. This program doesn't exist anymore then. So execve is another funny thing. So fork returns twice. You call it once, it returns twice. Execve, you call it once, it doesn't return. Something else happens instead. Exit does the same thing, right? That also, you call it and you never get to return. Okay, let's try that. If we're lucky, maybe we can actually see it. Oh, maybe we can see it do things in different order. Oh no, too bad. Okay, but anyway, we do see the mix, so that's interesting. Right? It says hello before, and then it says grep, and then it says the output of ls. Okay, so they're clearly running at the same time. Okay, but that's not what we wanted, right? We wanted to actually grep here. So let's just start with just running grep. See what happens. Should it be bin grep? Probably not. No. There's no particular rule for which goes where. Okay, so here's a... what did I want to grep for? I wanted to grep for everything that ends with .c, right? So now we need to pass in parameters to grep. And I'm not allowed to say this, right? Or even like that. Because that's not a binary. So on the command line you do one thing, but we are supposed to specify the path of a binary here. So now we need to create this array, our new argv that we want to pass in. And notice another curious thing here. I'm not actually telling execv how long this argv is. So how does it know? Doesn't matter if it's on the heap.
There's a heap, you know what the size is.
Ah, yes, well. First of all, it's clearly not on the heap because it's... Oh, it's a pointer. Yeah, so that's right. It could actually be on the heap. But there's no guarantees that this was allocated with malloc. It could be anything. In fact, we're going to put ours on the stack now. No, that doesn't. That's not it. Yeah, someone's been reading up on this. Yeah.
You do that on the first, like, when you map in /ls, like, you created RB and then, like, had parentheses apart on a 0. So
Oh, maybe. Yeah, I don't remember this, but yes. So there's a neat little trick there. I don't know why they decided to do it that way. It's not necessary. They could have gone with a count as well. But argv always ends with... So if you go argv 0, that's the name of the binary. Argv 1, first argument. Argv 2, second argument, so on. And then eventually some argv is going to be just a 0. It's a pointer, but it's 0. And that means there are no more arguments. Okay, so it's a variable size argument without saying anything about the size. So we will need to create one of those. So let's just make that. I'll call it like... I think it's enough to have... Oh no, we need 3 slots in it. So it's an array with 3 character pointers, right? So what's the first one?
Grep.
Very good. Arg0 is grep. Why?
Because we know that they're going to be the first in the program.
Yeah, what happens if I say it like that instead?
It's probably
Still
still going to run.
gonna run. If grep for some reason was to read arg0 to see what its name was, then it'll think it was called grep. Okay. So when a binary runs, it doesn't know where it came from. It just, there's some image that's in memory and it's running that. It doesn't know which file was read. So this is the only way it can figure out where it came from. Of course, it's not actually called, I mean, that doesn't specify it completely either. It would have to be user bin grep if it was to find itself again. But what's the point of that? If you want one more of yourself, you don't go and execv it, you just fork. Okay, so that's one. And then we want a pattern, point C, to look for, and then 2 is nothing. Okay, so now we pass that in, and no environment variables. We don't need it. grep doesn't really care for it.
For 2 of the environment variables, you could look in every directory for C, for .c.
Look in every directory. Well, that's not how grep works. So grep looks on its input for whatever's in the first argument, or all the arguments, I suppose. So it doesn't care about even where that is. It doesn't know about files. If you say, oh, it can know about files. If you say grep something and then a file name after, yeah, then it'll open that file and look through it there. But the environment variables still aren't used for that. Okay, so what's going to happen here? Let's try it. This is still a little broken, but let's see. Hey. Oh, I'm still editing the one that's in the wrong directory. Okay, so let's compile that instead. Okay. So what happened there? So now,
I didn't know what to search through.
so it's supposed to read from somewhere, grep here, and eventually,
Will it just run whatever's in that folder? No.
it runs grep.
Yeah.
Grep just got upset. I think it got upset because it had no one to talk to. Let's see if we, actually I'm not sure about this, but let's try just giving it some input. Oh, now it's pretty happy. But of course it doesn't end with .c here, so if I say hello.c, oh, there it is. Okay, maybe, all right. So grep, so we made a clone of ourselves, right? So that clone has access to our standard in, but there wasn't anything on standard in initially here. So grep didn't like that. Right? It's supposed to get something. And for some reason now, I can't really explain this well. I didn't get it from the command line. That must be something with the implementation of the shell. I could also go like this. Right? So grep is talking to the standard in here now. It's happy. And now I'll quit my standard in. I close it with Control D, and that makes grep quit as well. Okay, so that's a good start, but that's not what we wanted. We actually wanted to grep on this output, have grep listen to that output and look for .c's in there. So we don't have. I wish there was line numbers on here, but we need to make a. Yeah, I know, but I want to show the line numbers because now I want someone to say, where do we put our pipe?
Need Vim.
I need Vim, yeah, exactly. I just am not a VI user. I could use Emacs, but I don't like using Emacs in lecture for some reason. It's just so much stuff going on in Emacs. This feels a little more constrained. Okay, so we need a pipe, right? We need our ls to be saying things to grep. Where do we call pipe? Let's take a look at this again. Man to pipe. Any thoughts? Let me just scoot down here, and someone can just holler. What's it? Holler back? No, that's not it. Someone can just tell me when I should put my pipe.
Just before the fork?
Just before the fork.
Oh, we definitely need two processes. Right?
What's that? We definitely need two processes. Okay.
Yeah, pipe needs to talk between two processes.
So you're thinking after the fork, and we had a couple of people thinking before the fork, I think.
I'm like this a bit.
When you fork, does it create a copy of the file descriptors you have to do?
So when you fork, you get copies of everything.
I figured that you need to actually just based on the F statement change things.
Yeah. So the problem here is, if we were to put the pipe over here, what happens? We get two pipes. Two pipes that are not connected to each other.
Oh,
So that's not very helpful.
so probably after we oh no, never mind.
Now we got to put the pipe up here. Pipe ends. Call it that maybe. And then we'll say pipe. Okay. So now we have a pipe, And now we fork, so now we have two different processes both looking at the same pipe. And they have both ends of that pipe as well. So now I'm ls, right? If I'm ls, I ought to be writing to the right end of that pipe instead of to standard out. So ls doesn't know, remember, ls doesn't know about other file descriptors, but if I open some new file, I can't tell ls to go writing to that file. ls always writes to standard out. Or that is, it always writes to the second entry in my file descriptor table. Standard out isn't anything in particular, it's just the number 1 is standard out. So I need to make the number 1 mean something different. What I'll do is I'll say dup2, and then I'll have the index that I want to copy. So which one is that? That's the right end of the pipe here. So number 1 is the right end. And I'll put that on standard out. Okay, so now I'm writing there. Actually, why don't we see what that does?
Dup2 knows that standard out is 1. You don't have to
Do
say
we need to fill pipe ends to with anything?
You know, I'm not sure that standard out means 1. Isn't that a file pointer?
That's
It
not
probably
standard
is,
out.
yeah. So that's no good. You have to you have to do something like file des standard out in order to get the number. So that's nonsense. Let's just go with a 1. Okay, there was another question?
Do you need to fill int pipe ends to with anything? At the top.
No. It's just an array that pipe is filling.
Oh, it's filling. Okay.
Yeah. So this is the same thing here because it's an array. That's the same thing as saying that. So pipe fills those values in. Okay. So now I wanted to do this. Yeah. So that's good. That's what you caught, right? The file pointer. You can't make that into an integer. So I put the number instead. Okay. So if we run this now ls is writing to the pipe. So what do we expect from output? Doesn't work so well, right? The stuff got written into the pipe, but there wasn't anyone listening at the other end of the pipe, so what good is that? So to be nice here, we're also going to close pipe ends 0. Because ls is not going to be reading from this pipe. It's only writing to the pipe. And then at the other end, we'll say dup2 pipe ends 0 to standard in, which is 0. And then close and 1. Same thing, grep is not going to be writing to this pipe, but it will be reading from the pipe, and it only reads from standard in. So now we have done our redirection, and then we're ready to take it for a spin. There it is. Okay, so why does it say pipe.c there? Only because we have a file called pipe.c in there. So let's make another one. Okay, so that's pretty much it, and we're also out of time. Questions on this? Okay, so every piece is not so complicated. What's complicated in this homework is you're going to have like sometimes a longer string of pipes going on. There's some recursion required, and then of course you can also go like this. File.txt. All right, and then we expect output to show up in there. Yeah.
The close commands you use, is that what you were talking about? If you didn't close it, it would just stay open.
Yeah, it'll get all confused then. In this case, I'm not sure it would actually happen, but certainly in the shell, sometimes that does happen. And then you go forking again, and suddenly you have all these different file descriptors all over the place. You've got to practice good pipe hygiene. Okay, so see you Monday.